Well, it's my pleasure to introduce to you Scott Williamson, VY1SW. Scott is the Vice President of the Yukon Amateur Radio Association, for which he does a tremendous amount of work on the repeaters and a new trailer that the club is making at the moment, and many other things. For one of our club meetings just a few months ago, Scott made a presentation on Lithium-iron Phosphate batteries that was really interesting, and lots of information that would be of value to amateurs. And he's going to present this topic today. Scott has been an amateur radio operator since 1991, and he's been very active with the Yukon Amateur Radio Association since moving to the Yukon in 2003. He has been a part of the team that has built the Yukon's linked repeater network, which currently consists of 21 sites covering the southern half of the Yukon into British Columbia and as far south as Juneau, Alaska. He is an expert on 12-volt systems and many other things, I think, especially remote repeater sites and RVs, and is also an avid outdoor adventure seeker, competitive curler, and certified curling coach. So with that, Scott, I'm looking forward very much to hearing your presentation once again.
Appreciate that, Alan, and welcome everyone. And as Alan mentioned, YARA has a bunch of real interesting repeater sites. The photo in the background there at the start of the presentation is one of those sites. Surprisingly, after our discussion about winter, that picture was taken in May. So you get some ideas of some of the conditions that we're up against in the remote mountainous north here. So anyways, so today's topic is about lithium iron phosphate batteries, and really this came about, started as a study that I did when looking to replace the 12-volt batteries in my RV. And as I delved deeper into this and started collecting data, I realized that there were very definitely applications for YARA, specifically because we have a significant number of off-the-grid solar and wind generator powered remote repeater sites, and having improved storage is becoming more and more significant, especially with the sort of the modern radio systems, and not so much impacting our radio gear, which we tend to use sort of older, very power friendly stuff, but a lot of our site partners are upgrading to newer radio gear that consumes a fair amount more power. And we're sort of at a place where we need to start thinking about how we expand that capacity, and especially so that these sites can survive through a long and fairly dark winter. Oh, looks like the sharing just quit. Host disabled participant screen sharing. Okay, well, let's try it again. I'm unable to share my screen at the moment.
Scott, I'll see what I can find out. Just one moment.
Okay, thanks. Yeah. So anyhow, so this is
in that room. Can I ask what your name is, please?
My name is Arthur Smith, BY2BIT.
Okay. When you come back, I'll get you renamed. Okay. Okay. So I'm gonna put you into that room.
Trish, the screen sharing died on room 4.
Okay. I'm going to go in and just make sure that it's okay. I've done the screen share again.
Okay,
Alan, I think Alan may have the same.
Yes, that's right.
Yeah, 1 second. Let me just, okay.
So you fellows going back into those rooms?
Yes.
Sort of the traditional, oh, it just stopped again. And host disabled participant screen sharing again. So compared to sort of the more common sealed lead acid.
This is, okay, so Alan still got problems?
Alan, you should be okay now.
Okay, thank you.
Just go in and don't touch anything. I've changed it.
Yeah, thanks very much.
Sealed lead acid style batteries, and specifically in sort of the 12 volt capacity, which is, I guess, very common both in terms of the amateur radio and repeater gear that we're using, and certainly as it applies to sort of RV systems and so on. So just some key differences. Usable capacity, when you're comparing amp hour ratings of battery, is typically 30 and maybe more like 50% more. And we'll get into a little more detail on why that is, but essentially, if you buy a 100 amp hour sealed lead acid battery, you really, if you want to get full life out of that battery, you really can't draw it down below about 50% depth of discharge. Whereas with the lithium iron phosphate technology, you can pretty much use 100% of that rated capacity. So the usable capacity is quite a bit more. The life, or the number of cycles that the batteries are good for, even at that full depth of discharge, is somewhere in the neighborhood of about 3 times more, or even more, depending on how much discharge the application uses. The cost for the rated capacity is probably between 30 and 50% more. That's changing rapidly. And in fact, some of the numbers that you'll see in this presentation, which I put together a couple of months ago, have changed dramatically even since then. So that is something that's rapidly changing. And the weight of similar sized cells is probably a half to a third of a similar rated AGM or sealed lead acid battery. So just in terms of chemistry, so lithium iron phosphate batteries, they refer to them as a rocking chair style battery. And essentially lithium ions move from the sort of the negative to positive electrode when charging, and then back, or when under load, and then back when charging. So you can see in the diagram here, sort of you have the carbon or graphite layer. Under load, these lithium ions are moving into the phosphate layer, and then under charge, they reverse that process. And it's a pretty simple process in each direction. And as a result of how that works, they're inherently very efficient, and the discharge voltage curve is also very stable. So you can see here's a graph of a typical lithium iron phosphate, and it's somewhere, and generally lithium iron phosphate comes with a group of 4 volt or 4 3.3 volt cells to produce sort of your 12 volt equivalent cell. And generally full capacity, they'll be around 13.4 volts. And they don't start dropping until well over 80% of capacity. So your entire kind of usable range of load range is all within 1 volt of sort of the optimal voltage. So that you see very little. They're also not subject to the same kind of sagging that you see from a sealed lead acid that's under load. So sealed lead acid under load will read a lower voltage than one not under load, whereas these are very constant. And make for a real stable platform for equipment. In terms of just general capacity, so most manufacturers of 12-volt batteries basically recommend a maximum discharge to about 11.8 volts, which if you plot that similar graph to what we saw in the last slide with an AGM is really about 50% depth of discharge. The 11.8 volt point is also generally recommended by lithium iron phosphate manufacturers, but that's more like 90% depth of discharge. And so below is some data readily available on the internet of some testing that was done. And this is comparing both an 8 amp load and an 80 amp discharge load on somewhere in the neighborhood of 400 amp hour rated capacities of sort of 4 12-volt 100 amp hour lithium iron phosphate batteries versus 3 different examples of an AGM sealed lead acid battery, as well as a sort of more common golf cart flooded 6-volt, 4 6-volt batteries connected such that supplying 12 volts and delivering a rated capacity of 420 amp hours. And you can see from with an 8 amp discharge rate on them, the delivered capacity to that 11.8 volt level, you would get 108 amp hours of actual delivered, 108% of the rated capacity out of the lithium iron phosphate, about 60 to 70% capacity for the lead acid or the AGM batteries. And when you go to a higher discharge rate, which probably isn't common in terms of like our remote radio sites and so on, the bigger discharge. But for instance, in an RV, when you're running an inverter, oh, there goes the presentation again. And the host has disabled participant screen sharing again. So when
Hi, Alan.
Hi, Trish. Yeah.
Yeah, what happened?
The screen sharing has disappeared again.
All right, it's there.
Thank you.
Trish, we lost screen sharing again in room 4.
Yeah, it's taken care of.
Okay.
load increases. Oh, and here we go. I can share again. Next, I'll talk a little bit about the life or the cycles available. So a typical AGM or sealed lead acid battery, depending on the manufacturing and the process, is 900 to 1500 cycles in that 10 to 50% of depth of discharge range. And it's somewhat constant as long as you keep it above that 50%. So if you discharge them more than 50%, you do start to impact the number of cycles available. Lithium iron phosphates are typically 3,000 to 4,000 cycles at 90 to 100% of discharge. And the interesting thing, though, is that they increase in a very linear fashion with a lower depth of discharge. So if they were 4,000 cycles at 100%, they'll be almost exactly 8,000 cycles at 50% and 12,000 cycles at 33%. So it's using just the top part of the battery has dramatic improvements on the number of cycles. So essentially that rocking chair chemistry has a finite number of times that the lithium ions can move back and forth. And if you just move a few of them and move a few of them back, then the number of times you can cycle that entire battery increases in that linear fashion. Obviously, this technology is fairly new. There has been some studies and some extrapolation work done. They're predicting that they have an actual sort of physical lifespan of at least 20 years. we'll know in another 15 whether that's really true or not. But it's anticipated that even if your application doesn't exceed the number of cycles, after 20 years, there's some possibility that there'll be other degradations impacting their performance, such that you might never get the number of cycles out of it. And just, I mean, anecdotally, I replaced the batteries in my camper this year with lithium iron phosphate, and my expectation is they're quite likely the last batteries I'll ever buy to put in that camper, given that data. When you start looking at cost, and again, these numbers are changing fairly rapidly right now, but when you start talking about the cost per watt hour, and based on that data from the earlier chart with the delivered capacity, you start to see that sort of those 400 amp hour lithium iron phosphate batteries, though pretty much twice the price, the cost per watt hour is certainly not that much different. So you're looking with an 8 amp load, which is sort of an easier comparison for the AGM and flooded, which perform very poorly under the bigger loads, but you're looking at 66 cents per watt hour versus sort of close to 50 cents for the sealed lead acid AGM, or 15 cents for the flooded. Well, when you start to take into consideration the number of cycles at that capacity, you start to see that cost factor starts to flip fairly quickly. And like I said, when I put this chart together, in Canada, 400 amp hour lithium iron phosphates were $3,720. I noticed just a couple of days ago that the 100 amp hour cells that I put in my RV are now $750 each, which puts you down to about $3,000. So this equation and benefit case here is rapidly getting better as time goes on. So that cost is becoming less and less of a close comparison, and the distance between them starts to get pretty substantial pretty quickly. Talked a little bit earlier about the weight of them. They're significantly lighter. So in terms of bigger arrays of batteries, obviously there's less concern with loading on floors and those kinds of things. Handling is so much easier. The 2 batteries I put in my camper recently are 26 pounds each, and the 2 I took out were 80 pounds each. So I basically put my camper on a 100-pound diet just through the switch. And you can imagine the battery compartment on my camper is probably almost 6 feet off the ground when it's sitting on the truck, and lifting those 80-pound batteries in and out was always a serious chore, whereas these 26-pounders, it was almost a non-event to take them out when I was putting my camper to bed for the winter here a week ago. So real substantial weight difference. They're also fairly easy to handle in terms of shipping. They don't require any sort of special handling. Most manufacturers, when you buy these batteries, will ship them to you for free because they give them to Canada Post, and Canada Post delivers them. So it's the whole sort of complications around handling batteries gets very simple with them. Talk a little bit about charging, and basically the lithium iron phosphates are much more efficient at converting charge energy to usable energy, and sort of the whole efficiency cycle is somewhere in that 95 to 100% range for lithium iron phosphate, versus AGM are about 80% efficient in that charge discharge rate. So you're actually gaining almost 20% when you're talking about solar powered systems or whatever. The amount of energy required in is almost 20% less with the lithium iron phosphate to get the same usable energy out. So this graph at the side is a plot of charge over time. This is a 40 amp charge into a 100 amp hour capacity battery, and a single 100 amp hour lithium iron phosphate versus a 200 amp hour AGM that's at 50% state of discharge versus 100% for the lithium iron phosphate. So try kind of a like for like comparison in terms of the number of amp hours to replace. And you can see the red line, the AGM, there's the charging happens a little faster up to that full sort of fully charged voltage, but then there's a long absorption phase required when charging AGMs for them to maintain that voltage after the charge goes away. So the total time to charge the AGM in this particular example is a full 5 hours for them to be at their 100% state of charge. Whereas the lithium iron phosphate, they take a little longer to get to that full rated capacity, but essentially the moment they reach that voltage level, they're full and you can stop charging. So the amount of time required at 40 amps of charge is 2.5 hours versus the 5 hours for the AGM. So kind of a real dramatic difference when it comes to, like I said, off the grid systems, especially where the amount of time required to charge the AGMs obviously is twice as long. And we know in the north here, especially in the winter, there's not too many hours of solar available. So the quicker that that process can happen, obviously, certainly a significant advantage here. Few other sort of considerations to kind of talk about. So most or essentially all lithium iron phosphate batteries require a battery management system or BMS. And when you're tying the 4 cells together, essentially the job of the BMS is a few things. One is to keep all 4 cells balanced and sort of equal in terms of voltage. They also typically will provide other protection, and that's against charge and load when over temperature or under temperature. I guess some of the BMSs aren't that sophisticated, and that's something to watch for when acquiring these, but and we'll talk a little bit about that in a minute. The self-discharge rate of lithium iron phosphate is a whole lot less, and sort of typical is about 3% per month versus an AGM, which is about 2% per week. And some of the batteries, the ones I bought for my RV, for instance, they have a system that will turn off the BMS and kind of put the batteries into sleep mode. And when turning off the BMS, that self-discharge rate, they actually say they lose about 3% per year with the BMS disabled. So again, for storage or if you have a battery that's sitting to use as a standby power source or whatever when the power is off, they require very little energy to maintain them in their ready state. And that's because of the dramatic difference in internal resistance with the battery itself. Charging parameters for lithium iron phosphate is very simple. There's no equalization or absorption phases required. Essentially, they want constant voltage until they're full. Typically, the BMSs in them will turn them off once they're full too. So you can simply apply a 14.2 or 14.4 voltage source to them, and when they're full, they stop charging, and that's that. AGMs, require sort of much more sophisticated charge controllers, bulk phase, absorption phase, float mode, and temperature compensation as well, whereas none of that is required with the lithium iron phosphate. There's no off-gassing or ventilation requirements. There's no maintenance requirements. So one of the limitations with the chemistry is they cannot be charged when colder than -2 Celsius. And in fact, most of them are set to block charging if it's below 0, just to keep them safe. And essentially what happens with the chemistry, if it's below -2, the lithium ions, instead of absorbing to that carbon as part of that rocking chair process, they electroplate the carbon. And that, as you can imagine, is a bit of a catastrophic failure in terms of the internal workings of the battery, and is very destructive. And you might get away with a very low amount of current for a short period of time when it's colder than 2 Celsius, but essentially the batteries are destroyed if you attempt charging them when colder than -2. And there's some ways of mitigating that. There are quite a few manufacturers now producing sort of packaged batteries with heating elements in them that will divert charge energy to heating plates in them until they're up to enough temperature that they can accept the charge, and then they begin charging. So there's ways of handling that. That makes them a little less efficient in cold, but still potentially usable. As mentioned earlier, cost difference is somewhat negligible due to that watt hours delivered being almost doubled. So if a lithium iron phosphate battery is twice the price of an AGM, well, the usable capacity is typically double too. So you're getting into the ballpark of being very similar cost per watt hour. You can build your own lithium iron phosphate batteries by buying the raw cells and buying a BMS and putting them together yourself. I would say generally you can build one for about half the cost of a packaged cell as well. So for those of you, which many of us are, inclined to doing projects and experimentation and building stuff, that is an avenue that allows you to actually construct these for significantly less, and probably even then cheaper than or into the realm of the same price as a similar AGM battery. Another real benefit to the equipment that's connected to it is the voltage is very stable under load. So just anecdotal evidence on that, my AGMs that I had in my camper, if the furnace was running, which is about a 6 amp load, and the lights were on, which is maybe a couple amp load, and you turned on the water tap slowly so that the water pump was surging, and it draws about 10 amps when it's on, you could see the lights dimming as the water pump surged with the AGM batteries. With the lithium iron phosphate, the voltage is absolutely rock solid, regardless of the amount of load on them. It doesn't sag at all. And that makes it a whole lot easier on electrical systems and so on that obviously would certainly prefer having that stable voltage supply. So that load sag isn't a factor at all with lithium iron phosphate. So just a couple of sort of conclusions, I guess. Recap, actual installed cost is probably about the same. Life is probably 3 to 4 times longer. Handling is a whole lot easier, and charging is much simpler. So that's kind of wraps that. And so just kind of a couple of pictorial comparisons here. So these those eliminator batteries there are the AGMs, 100 amp hour AGMs that came out of my camper, and the ones that I replaced them with are shown in front, the lithium iron phosphate. And like I mentioned earlier, the AGMs that came out were 80 pounds each, and the new ones are 26 pounds each. So sort of handling and dealing with them is certainly radically different. Looking at YARA's kind of requirements for a typical repeater site, on the right-hand side, you'll see the AGM batteries that we're currently using in one of our typical off-the-grid solar charged, sometimes wind generator charged sites. So they're obviously 6 cells. Those cells are about 90 pounds each. The whole weight of one of those frames is 620 pounds. The two of them together, obviously, you're into 1,240 pounds of weight. The usable capacity of them is about, they're rated at 610 amp hours, but their usable capacity is about 300 amp hours each. They have a cycle life at that 50% depth of discharge of about 1,200 cycles. And the last time we bought them, 2 of them were where they were $3,800 each, and it cost us $1,000 to ship them to the Yukon. So we were into a cost of about $8,200 for that. Dimensionally, they're 40 inches by 8.5 by 23.5. So substantially large, very difficult to handle. You have to dismantle them into pieces if you have to move them by hand. For our sites, it requires significant helicopter time because we have to fly people up, and then we have to sling batteries up, and we need people on the ground and people at the site to receive them, and then we have to dismantle them, pull each cell out to move them into place. And those of us dealing with them for the next 3 days hobble around like our backs are done from dealing with it. So certainly a significant chore in terms of handling. Just as a comparison, there's a company out of Vancouver called CanBat that makes a cold weather lithium iron phosphate battery, and these are ones that have heating elements in them, so they automatically divert charge energy to heating them if they're below that -2 degrees Celsius or 0 degrees Celsius, as I believe how these ones are set. They make a 300 amp hour 12 volt cell, so 2 of those, and they obviously you can use 100% of their capacity. They have a cycle life of 2,500 is that manufacturer's prediction at 100% depth of discharge. Obviously, if you cycle them less than that, the number of cycles increases. Right now, they cost about $3,100 each. They don't charge shipping anywhere in Canada, so a total cost of $6,200. And each one of those cells weighs 76 pounds and is about 20 inches by 8.5 by 10.5. So the handling of them is very simple. In fact, we could set them on the floor in the back of the helicopter where we're sitting while we fly up the mountain, and could carry them and deploy them without requiring all the slinging and complications that come with that. So kind of a dramatic change, I guess, in how that looks like it'll apply to one of our sites. So that's kind of it for the presentation, and I see we've got about 15 minutes left. Happy to answer any questions. There's probably been some chatter on the chat, but I'm really good at talking over any chatter, so feel free to unmute and ask questions, and I can flip the slideshow back to a particular slide if you wanted to look at it in more detail. Yeah, welcome any and comments.
E4HAY.
Go ahead.
What is the fire rating of these batteries? Like, do they start on fire like other lithium?
So the lithium-ion technology is very sensitive to pressures and internal shorting, which is what's led to sort of fires on aircraft with phones and all those sorts of things. The lithium iron phosphate chemistry is inherently very stable. If you do some searching, I found a few YouTube videos of people shooting them with guns, chopping them with axes, exposing them to fire, and lithium will burn if it gets hot enough. But generally, the chemistry is inherently very stable, and so they are very easy to handle. B, don't require, like I said, you can put them in a box and go to Canada Post and say, mail this, and you're not breaking any rules doing so because they are inherently very stable.
Thank you.
As long as you don't short
Thanks, Derek.
I would.
Yeah, obviously shorting a battery is bad. Again, with the BMSs that most of these batteries are equipped with, especially if you're buying a manufactured cell, you can, the BMSs are designed to protect them against something like that. So if you short them out, the BMS will likely disconnect them fairly rapidly to minimize the risk from that. Second, I mentioned those batteries that I bought. They actually have a couple of they look like Ethernet ports on the top of them, and they come with a little switch that you plug into one of those, which will turn off the BMS and disconnect the load from the battery to put them in. They call it shelf mode or sleep mode or something. And once you do that, you can short the terminals on the top, and there's no load there because they're disconnected. And in that state, that's where that manufacturer says they lose about 3% a year in charge. So that's a great way to kind of put them in storage. And obviously, if you were shipping them or even just pulling them in and out of the camper, handling them, I put them in sleep mode. So then I didn't have to worry about bumping the terminals on wires or whatever as I was maneuvering them out.
It'd be wonderful if they got them into all these cars that are on the road. I was a firefighter, and I did a lot of training with the electric cars. And one of the biggest problems is they don't have a switch in the standard position. They're all over the car. Some of them you have to dig out. So that would be a great help. Two questions. One is in comparison to lead acid, or even the other question I'll be asking is gel cell. How do they react with temperature changes, low temperature, extreme low temperature, while they're still charged? Are you getting the amount of current out of them?
Yeah, so similar to sealed lead acid, or I mean, we use on our mountaintop sites AGMs, and those mountaintop sites definitely experience minus 40s in the winter or colder, and they similarly lose some capacity at colder temperatures. The rate of capacity loss is a bit less than AGM, but it's sort of in a similar realm. One of the kind of current sort of challenges or concerns with them is that there is some thought that when being discharged when colder than minus 20 Celsius, so we know they can't be charged to colder than 0, but at colder than minus 20, there is some speculation that there's some degradation in life of the battery, or the number of cycles if they're continuously used in that much colder state. And so one of the things that YARA is planning to undertake this winter, as Alan mentioned, we're building a new communications trailer, and our current plan is to put batteries in it that would be similar to what one of our remote mountaintops would require. And we plan to build a kind of a super insulated box to put them in, and install our own heating elements in that box to maintain the temperature of the cells either above minus 20 when they're just going to be under load, and or above zero all the time. And we're going to run a couple of different models and parameters over the winter and measure the amount of energy that's consumed by the heating element versus the amount of charge necessary and the loads and so on, so that we can really understand how to properly size them for these remote mountaintop sites. And the idea being doing that on the ground where we can access them during the winter, and we can easily connect them to the internet to post that log data out. We'll likely use APRS actually to feed that log to the log data to our website, so it's easy to monitor them and watch them before they're at a remote mountaintop site that requires a helicopter to get to, which you can imagine is when things go wrong on a mountaintop, the dollars mount very rapidly. So that's our intent, is to do that kind of study with them. And if you're interested, feel free to reach out to me, and I'd be happy to share some of those learnings next spring or whatever, once we have that information at our fingertips. Because I don't know, this technology is new enough. I suspect there's been some research and work into cold performance, and especially in vehicles, but I haven't been able to get my fingers on sort of any real solid data. And so collecting it ourselves, we kind of decided was probably an essential thing. And we're hoping to partner with one of the different organizations that share many of our repeater sites, and get some investment from them in terms of maybe buying the batteries, and we'll collect the data or whatever. So that's kind of something that's underway by our club right now, to try to get a real clear understanding of that. We think, just on sort of the back of the napkin calculations, that ultimately they'll still make way more sense, and cost per watt hour and capacity delivered and all those things, even with the element of heat having to be added to it. But obviously we want to test that in the real world before we live or die by that statement. So that's our intent for this winter.
The other one thing I was going to say was, you didn't bring in the talk on the gel cell batteries. I have been a proponent or user of gel cells in motorcycles. They last 10 times longer than, or not 10, about 50% longer than the regular lead acid battery, and they hold a good charge, and they're smaller too.
Yeah, we looked at some gel cell technology. They don't perform well in the cold. They are more susceptible to cold, and in fact, they can, if they're not fully charged and they get real cold, that can be a catastrophic event for them. They will split and crack their innards in that situation, because they do freeze and expand a bit when they freeze, which and that expansion varies based on the state of charge. So, and our remote mountaintops, when it's coldest, is also when the batteries are at their lowest state of charge, because of course we're dealing with wind generators that no longer work, and solar that's covered in ice and snow and everything else. That circumstance is keenly felt in the remote mountaintops. In fact, here, if it'll let me share my screen again. No, I can't share it anymore. Anyways, I was going to share a picture of a wind generator that's got about 8 inches of rime ice coating it, and as a result, you can imagine it doesn't do much when it's cold because of that. So, anyways, the gel cells are good, or a good technology on something like a motorcycle for sure, or a vehicle, and especially something that's not used in the extreme cold. and can be kept at full charge. I haven't specifically looked at gel cells, but a flooded cell, just as a sort of a comparison, I guess, at 100% charge, they freeze at somewhere around -46 Celsius. At 80% state of charge, they freeze at -20. And so that dramatic progression of state of charge and freeze point becomes real important, that you have those batteries fully charged when they're exposed to cold. And gel is similar. I don't know the real specifics of it in terms of temperatures, but they're subject to the same kind of limitations. So
Probably why I've got away with it. I just put a smart charger on it, leave it in the bike all winter long.
right, and so if as long as they're fully charged, there's probably little risk. So yeah, it's that remote mountaintop application that we're looking at obviously is something that has its unique challenges. We're also looking at APRS driven remote switching so that we can turn off several of our partners at sites and their commercial radio systems. Obviously they don't need them running in the winter, yet that their commercial repeaters use quite a bit more energy even when they're just sitting on standby than our equipment. So we're trying to come up with a way to be able to turn those loads off during the season when there's no charge opportunity, and that'll allow the capacity of the batteries to carry our equipment through. The repeater gear we use is made by a company called Daniels Electronics. It's several years old, but it's very energy efficient. A shelf, a VHF drop, and a UHF link on it draws about 100 milliamps on standby, which allows it with sort of that generally somewhere in the neighborhood of 600 amp hours of capacity of our existing power systems to survive the entire winter and still operate when we need it to, given the level of activity and so on it sees up here. But some of the new commercial stuff is drawing a couple of amps on standby, and that obviously chews through that capacity pretty quick as soon as you're no longer replacing that charge every day.
Scott, there was a question quite early in your presentation from Chris VE7UTV. I think you sort of answered this later on anyways, but he asks if there's a special charger needed for these batteries, the lithium iron phosphate.
Right, so they will definitely function on the same charger that is being used to charge a current sealed lead acid or AGM or flooded cell. They don't require all of those parameters that optimize charging for that type of battery. Generally, the BMS in the lithium iron phosphate will protect it from some of those parameters. So that long absorption phase, for instance, once the battery's up to capacity, it just shuts it off, so it doesn't accept charge anymore. So there's no harm generally in using those, but really the charge is you need a constant voltage with a current supply, and that's all that's required. And I think most of the batteries are either 14.2 or 14.4 volts constant until full and then off, and there's no temperature compensation required, and no float and bulk phase and absorption phase, and all that is unnecessary with them. So generally speaking, you can get away if you already have the charger with using that charger, but you can also install a much simpler charger to charge them, and they're even happier at that state. We've found, especially for our remote mountaintop sites, when you're combining an RF radio site with a lot of the modern charge controllers that are PWM, you have some challenges around radio interference coming from those PWM chargers, because they're switching power supplies that are turning on and off at rapid rates and creating a bunch of RF energy as a result. So one of the things we look forward to with upgrading our sites to this technology is a simpler charger that just provides charge and disconnect when full. And so solar controllers and that sort of thing are, again, a whole lot simpler and doesn't require the same kind of fancy parameters that the lead acid do.
Scott, I'm going to have to cut you off now because I understand there's about 30 seconds left before we're cut off anyway. So I just wanted to thank you on behalf of the conference organizers for such an interesting presentation. Thanks again, Scott.
Great. Thanks, everyone. And as I said, reach out if you have any further questions or want to be pointed at some more details.